Well, hello and welcome to Berkshire Guitar Amplifier Repairs. Stuart Smith with you as always, and we've got a couple of interesting amps in today. They are a stereo pair of quad 2 valve amplifiers. These are quite old now, and the customer's brought them in to me for a look over, and he says one of them seems to be a bit hummy, so we'll be having a look at that. So let's flip them upside down and get the bases off and have a look inside. Okay, here we are inside one, and you've seen one, you've seen the other one, so we won't bother too much about looking in the second one. Very simple, isn't it? There's nothing much to this amp. You can see we've got a rectifier valve. We'll flip it upside down in a moment and look at the valves. The rectifier valve, a pair of push-pull power valves, and a pair of preamp valves. I think they're EF86s in this amp. A handful of resistors, a couple of capacitors, a couple more capacitors here, and this, I wonder where the smoothing caps were. This is the two smoothing caps, so it's 16 plus 16 microfarads, so that's the ground terminal there, and here's 16 microfarads, and here's 16 microfarads. So if one of these has hum, well, I mean, both of them really, we're going to pull this component out here by undoing these bolts. See if we can get inside it. It looks pretty kind. I'm not sure how you get inside this. Obviously not this face or this face, possibly the bottom face. But anyway, we might have to dump this out, this component, and just put in two 60 microfarad 450 volt capacitors in there, because that will almost certainly be the source of the mains hum. So I want to know what the customer wants to do on this, because obviously I can kind of get it going for him, but really ideally I would like to replace those two capacitors, this capacitor, this resistor looking fairly cooked look, and this is a electrolytic as well, I think. That's 0.1 actually, so maybe change that one, and resistors are probably okay. I won't get involved in changing it if I don't have to, and yeah, that's probably all we need to do, but reasonable amount of work, of course. Nicely made, very good quality stuff this. Superb transformers, and yeah, just obviously a very high spec piece of gear. So I'm waiting to hear what the customer wants me to do. Does he want me to just get them going, or does he want me to do a bit of a refurb and start changing out a few of these rather old components? So I'm just waiting to hear if he wants to spend the money on that. Not sure what they're worth. I'll have a quick look actually, and let you know. Okay, for your interest, I've seen a couple on eBay. There's £600 each, or there's a pair on there for £2,000. So they're worth a few quid. So it's worth spending a bit of money on them. So I'm hoping that the customer will come back and say yes. I haven't gone in with a huge quote. I think it's £150 each or something to bring them up to spec. So that's not a fortune. Let's just flip them over and look at the valves that this thing takes. Before I do that, I might just show you the schematic. I managed to get the schematic online. Right, an excellent example of the schematic here. I haven't talked you through a schematic for a while, so why don't I take this opportunity to talk you through this, and then we can get on to turning it over and having a look topside. So if you're completely familiar with schematics, just skip forward 5 minutes or so. But I do know some viewers love to be talked through a schematic, so I will do that now. Okay, mains in, look, coming in, and interestingly enough, no ground on this main, so these chassis are not grounded. I don't know whether to sort of modify that or not, or just leave them as they are, but anyway, it's quite interesting that they haven't grounded the chassis on this. Comes into the mains transformer, various windings coming off, look. We've got 6.3 volt winding here for the heaters of the preamp valves and the power valves, and 5 volt winding for the heater of the rectifier. I forget now exactly why rectifiers have a 5 volt heater and every other valve has a 6.3 volt heater. Seems a bit mad to me, but anyway. GZ32, not a rectifier I'm used to using. It's quite an old one. And anyway, so basically this looks like a couple of diodes. So it rectifies the AC to produce a DC here. of a few hundred volts. My guess is 350 volts or something, and that is smoothed, look, by one of the capacitors in this can here. So one of the 16 microfarad capacitors is there, smoothing it to produce a nice smoother DC here. This goes to, it's a bit of a mess this actually, don't worry too much about that. Anyway, it goes to the primary of the output transformer, and the secondary of the output transformer, again a bit messy, just goes to the speaker basically. So this is your output transformer. There's a bit of feedback coming off here, we won't worry ourselves too much about that. Then sticking with the DC, oh here we are, 340 volts, look. That goes through a choke which does a bit more smoothing to make it more ripple free, and look, another capacitor here to do a bit more smoothing. So we've got a nice steady DC here. And there's the other half of that 16 microfarad capacitor in that can there. You've got two 16 microfarad caps in these cans. Right, I'm going to leap now to the input side. So the input comes in, it goes straight to a pair of EF86s. Again, not a valve I use a lot. I'm not totally familiar with it. Of course I am familiar, but for every EF86 I see 500 ECC83s. These are arranged in a kind of push-pull phase splitter arrangement, so you get a bit of gain. You don't need a lot of gain on this because it's a power amplifier. So basically this is acting as a phase splitter with a bit of gain. What do I mean by phase splitter? I mean it takes the AC in and it produces one sine wave here and an anti-phase sine wave here, splits them into two phase and anti-phase sine waves here to drive the power valves. And the power valves get driven in a kind of push-pull arrangement like this. So when this one pushes current, this one pulls. When that one pushes, that one pulls. And that puts the current through the primary of the output transformer, gets sent across the secondary, moves the speaker in and out. Simple as that, really. I'm not going to get too involved in anything more on this. That's pretty much all you need to know. Yeah, so that's the schematic. Let's flip one of these over and have a look at the top side of it. There's not a lot to see really, and the valves here are, for the power valves, a pair of KT66s, and here's our pair of EF86s in the preamp side. Quite a simple little thing. This is serial number 19597. Don't know if you can see that. I wonder what the serial number of this is. What do you reckon? I haven't looked. Would it be 19596 or 19598 or a completely different serial number? Let's have a look. Oh my god. Okay, well this is 5455. So completely different vintage, these two amps, but identical. So they obviously made this 14,000, is that right? 14,000? Yes, it's 14,000 amps later than this. So they made this one, they made another 14,000, and then they made this one. And let's just have a look, because that's very interesting. I expected them all to be a pair, those, but let's have a look. Look how similar they are. They are pretty identical. In fact, I'm hard pushed to see any difference between those two. So even the same make of capacitor, look, same one there, same resistor. These are all identical, vintage. That's a slightly different cap to that, but that's about all the difference I can see. So that's amazing. They must have cranked these out and made a lot of money. I mean, it's actually hard to believe, isn't it? They made 20,000 of them, at least. That's the latest serial number we've got. 20,000. That is a lot of power amps. I wouldn't have guessed they'd made that many. Okay, well, that's all I can do now until I hear from the owner what he wants to do, and I will rejoin you then. Just whilst I'm waiting for the customer, I thought I'd take off this capacitor, and it came off quite easily, but unfortunately there's absolutely no way into it. It's they are 16 plus 16 at 450 volts, yeah. And it's completely sealed, metal can, no obvious way into it. Obviously we can get a hammer and chisel in here and start, you know, chiseling down there to open it up. That's a pity that. I'm pretty sure I'm going to want to be replacing these two caps. So I think probably the best thing to do will be to leave this in here, obviously for authenticity's sake, and I can easily put a couple of 16 microfarad caps in here, you know, and just take them off of here and put them in here, and just leave this for kind of authenticity's sake. I mean, ideally I'd like to get inside here, and I think I've seen a photograph. Inside here is a standard CAN capacitor with its 3 terminals, you know, the usual sort of thing. And ideally it would be nice to get inside here and replace that, and then seal it all back up again so it looks nice and authentic. I don't want to be smashing this open and finding I've really wrecked it and I can't put it back to make it look nice, you know. So that's yeah, it's a bit of a shame, that. But anyway, there you go. Okay, I'm still waiting for the customer to come back to me, but I just thought I'd let you see this. I've now got this capacitor out, and there's no way into this. You can see that you know, this side here is welded to this bottom flange here, and that side there is welded to this bottom flange, and the bottom flange is continuous, so there's no way those will come out. You know, if I were to maybe put a chisel down there with a great big lump hammer or something, I might be able to prise open this side maybe. It depends what's going on inside here, but it would really mess this up. It's pretty well sealed in there. It's not designed to be taken apart. Our only alternative here is to leave this in as a kind of legacy thing so that it looks nice, and put a couple of 16 mic caps here somewhere in a way that I will have to determine, because this will definitely be past its useful time. It's probably, I don't know, 50 years old, I'm not sure, so they'll be well past their use by date. Okay, so that really is all I can do now until the customer comes back to me and says he wants to spend a load of money on it, and if he doesn't, not sure what to do. I think it'd be a bit silly not to, because it's worth a fair bit, and we may as well get it up to scratch. I'm just going to push ahead with this because I haven't heard from the client. So I've put the capacitor back in, and my idea is to get a bit of Vera board, put a couple of caps on it, something like this, and then attach that to, just probably glue it to the side there with these caps on like that, and then we can bring these wires round to there. So that's the objective. Obviously we're going to kind of surface mount these caps. I can't really be putting pins through here to solder them onto, because it's going to be a bit too close to here. Don't forget we've got 350 volts DC on here. I think if we use some hot melt glue or something to, I'll have a think about it. I'm not quite sure how to do this yet, but I might even put a bit of you know, wire over here just to hold them down, and some hot melt glue on there, and that will definitely keep those on there. And then we can just kind of araldite this to the side here, and I think that'll be a fairly tidy job. And it's all kind of reversible if someone really wants to. If someone can get hold of a vintage one of these or something, and it'll never happen, but we want it to be reversible if possible, since this is quite a vintage amplifier. So that's the plan. Right, there's the capacitors down with hot melt glue. Absolutely solid they are. However, I'm still going to put a bit of tin copper wire around them like that somehow to keep them on. Maybe one there and one there. And then that's ready for the next stage. Okay, here we go. I finished the little subboard. A couple of little pieces of wood there just to space off these pieces of wire here. And over on the other side we have our two caps. They've got hot melt glue down and some wire across to make sure they can't move. I've added these extension cables which we will take off over to the terminals, well, you know, over to these wires here. And of course this is eventually going to go in here. So that glue's not quite dry yet, so we'll just leave that for the moment, and then we'll glue it in there and then wire it up here. I think that'd be quite a nice, neat little job. So there we go, I've put that little board on the side there, and that's not going anywhere. And we've got the 3 leads here, look, which I will solder down to these 3 here. 1, 2, where's the third one? There. Those 3, so I'll just make those off with some sleeving going into there like that. And that's job done on that. Next thing, he's asked me to change the mains input. It's one of these strange, I forget what they're called now, these mains inputs. So I'm going to change that for a standard figure of 8 mains lead. I asked him if he wanted a 3-pin IEC on there, and he said no, so I'm just going to go with what he wants. And we'll put a phono, instead of this here, we'll put a phono plug in here somewhere, so that you can just plug in a phono. And then, as you know, we have these capacitors to change, and I've ordered up some replacement resistors. These are measuring okay, they're 180 ohms at 3 watt. They look a bit cooked, don't they? Look a bit past their best. So I'm going to put 180 ohm 5 watt in there. Change those 2, change that 1, change the mains and the input, and that will probably be all I will do on this. I might change that. In fact, that's a 0.1, yeah. I probably will change that too. Yeah, there we go. So just wait for the bits to come in, and then I'll rejoin you when those parts come. Okay, I've got the subboard connected up now, and I've left the terminals kind of bare because I just want to check the voltage before I put the sleeving on. So I'm going from ground to one side of the cap. We've got 295 volts there, so that's all okay. And ground to the other side of the cap, 300 volts, so that's all okay. I can now turn this off. Make sure that voltage has bled down a little bit. Surprisingly bled down a lot. That went down to nothing pretty quickly. Wow, okay. And now we can put this sleeving on here. Cool, that resistor there is chucking out heat. I can just feel it with my hand now. So, bit of sleeving there. Oh, I think I'll get my heat gun out. And here, like that. Okay, that's the HT side of things done. Because this is so neat, I think I might just put a cable tie around there. It doesn't need it, but let's keep it as neat as the original. Right, that's that. Now we've got some bits here that have come in. So this is the resistor for here. Yeah, that's pretty hot, that. 180 ohms I made that. Let's check if we still think that's true. Yep, 180 ohms. And these are supposed to be 5 watt. So the schematic calls for 3 watt. I think those were 3 watt resistors. Okay, so my plan is to cut off this resistor here, make a little J hook on the end of these stubs here, and then J hook this in as well, but then to put this capacitor here across the resistor like this, spacing it away a certain suitable amount so that it doesn't get hot. And then I will cut off this capacitor here and here, just cut it, and then I might put a little foam pad on there onto which this will go like that, so that just in case if anyone ever wanted to resurrect the original capacitor or something, can't imagine why they would, but then that stays in there, and I don't remove that capacitor. So that's the plan. I probably won't bother filming all that because a little bit tedious to watch, but I'll let you know when I've done it. Okay, well this is interesting. I've chopped out that capacitor actually. I thought it was held down firmly. It's a 25 microfarad, 25 volts working capacitor, that. Yet the voltage across it, across this resistor, interesting enough, is 46 volts, look. So that capacitor has well exceeded its working voltage, well exceeded. I'll put the new resistor in and then see what the voltage is. And I'm planning to put this 100 microfarad 63 volts in there. You know, look at the size comparison. This is over double the working voltage and 4 times the capacitance. Look at it compared to this. You might say, why are you putting 100 microfarad in? Well, the honest truth is I just happen to have some lying around. But increasing the capacitance of this will just give you a bit more base end. It probably won't be terribly noticeable, but it'll be better than a smaller one. So it should give a bit more base on the signal there. Right. So well, I'm going to put a new resistor in, I think, and see what voltage develops across the new resistor. I'd be surprised if it's much different from that. Yeah, interesting that. Okay, there's the new capacitor and resistor in, and let's measure the voltage. Yeah, I didn't think it would be that much different because it's the same resistance. So 44 volts, interesting that. So that had 44 volts across it instead of 25. That would not have done it much good actually, especially those older capacitors. So there we go, there's our new power resistor in and capacitor, and we will, something's burning actually, that resistor is burning. That's interesting. Getting very hot, that. So 44 volts across 180 ohms, that's interesting. This looks pretty cooked, this resistor. I'm just going to do a quick calculation on that. Right, so something wrong here, not sure what it is at the moment. So basically that's got 44 volts across it, which seems too big anyway with a 25 volt capacitor. So 44 volts across 180 ohm resistor, well the power is V squared over R, so it's 44 times 44, divide R, 180, and the answer is 10 watts, look. So that 5 watt resistor is dissipating 10 watts, which is why it's cooking. Right, I think what I will now do is we've got another one of these, I'm just going to literally swap them over and do the same test on the other one, see what's happening there, how many volts that resistor's got across it. Okay, here we are, here's the second unit. Power that up, and yeah, the valve is alight. So let's see what we've got in the way of HT. It's coming up, look. So yeah, 325, 330, similar to the other one, so it's not like the HT is different. So what have we got across this resistor here then? 28 volts. That's interesting. So why is that so much lower than the other one? Okay, so even with that we've got, call it 30 volts. 30 squared is 900 divided 180. Here's 5 watts exactly going through there, and that's a 5 watt resistor. So that's really not right. And why we've got 44 volts on the other one, I'm afraid I don't know. So I think I'm going to see if I've got the schematic for this. Well, good morning. I have slept on this and woken up with a plan, as is often the case. What's actually happening is these power valves are what's called cathode biased. So it's not an adjustable bias pot. The current comes from the HT through the output transformer, through this valve here, and down through here, and down through this resistor here. This is the one that's getting hot. And similarly with this one, look, the power comes down here through this side of the output transformer, through the valve, and back out around here. So all the current from those two valves goes down through this resistor here, and this capacitor is to bypass the AC. So this effectively looks like ground to AC, but DC wise, in other words, take that capacitor out, DC wise it's got a resistor in the tail here. Now it's a little difficult to follow this diagram the way it's set out, but I don't want to get into too many details with you, but here's the grid here, look, where the signal is being fed, and here's the grid here where the anti-phase signal is being fed. Don't forget this is push-pull. The grid of any power valve needs to be held negative with respect to the cathode. Negative voltage with respect to the cathode. You've probably heard of negative bias. So this point here has to be negative with respect to that. Now look, if current's flowing down through this valve here and through this resistor, this is going to develop a voltage across it. We know we've measured it, it's 44 volts on one of them and 24 on the other. So let's just say it doesn't really matter, 20 volts. Let's call this point here 25 volts positive. So the cathode is 25 volts positive, but we need the grid to be negative with respect to that to get the negative bias. Normally you'd hold this cathode at 0 at ground and then have a negative bias voltage minus 35 volts or minus 35, minus 45 coming in here, but because this is positive now, it's say plus 25 volts, we need to take this lower than 25 volts. So for example, if you took it to 0 volts, then we'd have a negative 25 volts on the grid, wouldn't we? So 25 volts positive on here and 0 on there is the same as 0 on here and minus 25 on there. So you can see how you get the negative bias here by effectively holding this at ground. Well, sorry, this one here I'm looking at here. So how do we hold that at ground? Well, it's kind of via here's ground here. Look, it's a bit difficult to follow. Here's ground here, 100 ohms, and it goes up through these resistors. So the DC on here is 0 volts DC. There's no other way that a positive voltage can get in here. It's blocked by this capacitor here and here, and there's nothing. This is just going to the grids of the F86, so there's nothing there either. So this is held at 0 volts DC by this arrangement here. This is plus 24 volts, 25 volts DC, therefore this is negative with respect to that. I hope you're following that so far, and that's all good, that's what we want. Now if we wanted more current to flow through this valve here, and hence down through here, by the way, don't forget this is what we're interested in, then we would need to take this more positive than 0 volts. So if we took it up to plus 5 volts, for example, now we've only got 20 volts across here. The valve turns on harder, more current flows through, more current goes down through this resistor. So that's what we've got. We've got an error here. They're saying this is a 3 watt resistor here actually. Actually, I tell you what's quite interesting. I'm just going to sidetrack for a moment. See, they've actually written the voltage here that we're expecting, 26 volts, which was not far off what we got on our second amp. So they're looking for 26 volts on here. Let's just see what power they're expecting there. 26 squared is 676 divided by the resistor, which is 180. That resistor is 180. That's 3.75 watts. So this amp here is badly designed. They have a 3 watt resistor consuming 3.75 watts of power, assuming everything's good, which is nearly a watt over what it's rated at. So that's why that resistor, here it is here, look, is cooked. So I don't know what's going on there. Simple Ohm's law tells you that this resistor is not correct at 3 watts. Right, so that's a little sidetrack there. Anyway, as you know, on one of the amps we've got 44 volts here, so something's happening. Too much current is going down through here, which means that the grid is not 0. It's +5, +6, +7. We don't know. We can actually measure it and see what it is. In fact, we'll probably do that. So now, what would cause that grid to go from 0 volts? Don't forget, it's referenced down to 0 via this resistor here. There's ground. There's the 0 reference. It can't get any positive voltage from anywhere else. It can't get it through here. Can't get it through here. That's just a grid. And back here, look. Well, this is a ground. Look here. So it's not getting it through this resistor, and it's not getting it through here because this just goes off to a couple of grids. So where is it getting that? Assuming it is, where is it getting that positive voltage from? I think I know where it's getting it. By the way, we haven't even measured it there yet, but I bet you this is not 0. I bet these grids are not 0 when we come to measure them. I think these capacitors here are leaking. Don't forget, look, we've got 115, here's his HT here, we've got 330 volts here, and via this 180k resistor we've got 115 volts DC on each of these anodes. So we've got plus 115 volts DC there, in theory ground there. If this capacitor was leaking a little bit, it would be very easy for a sniff of that 115 volts to come onto here. You want a few volts, you want 5, 6, 7, 8, 9, 10 volts on there, and suddenly this grid's been taken positive, the valve is turning on to hard. So my money is on those capacitors, which by the way are these here, look, being leaky. Now we've got to be a little bit careful here because I don't want to be turning this on too long and measuring voltages because this resistor is getting 10 watts through it. So what should we do? I think I'm confident enough to just cut this capacitor here and here, and then we'll get the high voltage tester, what's called a mega, on there to see if that capacitor is leaking. I think that's probably the easy solution here. What could we? I suppose we could quickly turn it on and just measure. Let me see, 1, 2, 3. Which is the grid, I wonder? Okay, pin 5 is the control grid, and here we go. There's a little spigot there. We count clockwise from there. 1, 2, 3, 4, 5. So there is the grid there. That should be at 0. I think we could probably risk getting it all set up, kind of literally clipped on there, or one of them, and turn the amp on and see if we've got any voltage there. We should have 0 volts there. Okay, we're set up here now. I'm measuring on one of the grids, look, pin 5, and I've just got a couple of crop clips going off to my meter here, and we're set to 20 volts. So we'd expect to see 0 volts on there. So let's just plug it in and see what happens, and we'll be ready to disconnect quickly before this power resistor cooks. Oh, immediately look, we're seeing 5, 6, 7, 8, 9. It's coming down a bit now. In fact, it's varying at 12, 30. Oh, crikey, 70. Whoa. 30 volts there. Oh my God, no wonder. So we've got 30 volts DC. I'm just going to try the other pin 5 now on the other power valve. Let's see if that one's the same. There we go. And again we've got 30 volts there. Oh, that's absolutely hopeless. So that means that these capacitors here are leaking, and that's why that KT66 is pretty much full on and putting way too much current down through. Actually, interestingly enough, what's happening, because this is cathode biased, this amp, what's actually happening is instead of 0 volts on here, we've got 30 volts. And so this point here will rise, enough current will flow through here until this voltage rises enough to go above the 30 volts, say by 15 volts to 45 volts or something, to turn this valve not off, but to keep the thing ticking over at that current. It's a kind of automatic thermostat feedback. And so that's why we've got 45 volts on here, because we've got 30 volts here, which means this is negative 15 volts compared to this, which is not very negative, and so this is drawing a lot of current and you know, turning on this. So that is, I'm very pleased with it to know that's exactly what's happening. So if we now change these two capacitors out for a decent some orange drop 0.1s at least 350 working volts, you know, we're good to go there. So let's see what I've got in my stash box. Okay, so I've got a couple of decent orange drops here, very good capacitors these, and they are the way to read that is 104, so that's 10 with 4 zeros on the end of it, and that's 100 nanofarads or 0.1 of a microfarad, and they're 600 volts, look, so they're well overrated, which will be fine. So I'm going to drop those two in there, and then we will turn it on again. I bet you anything you like we measure 0 volts on those pin 5s. Okay, so we're got the two caps in and we're on, and now we're measuring across this resistor, and we have 24 volts, which is precisely what the 26 volts it's called for on the circuit diagram. So we've got 24 volts across there, which if you remember is about 3.5 watts. This is a 5 watt resistor, so we're good on that. And now if we measure the grid here, we've got no voltage there, very low voltage, 0.001. So these caps here, I think what we'll do is we'll get the mega out just for fun, and we'll just test the leakage on these caps. So these were both leaking. Obviously we're going to need to change the caps in the other amp as well, but I'm just concentrating on this amp for the moment. Right, so that's good, and that resistor's not cooking anymore. I can put my finger near it, it's not, I can feel it's slightly warm. So just for fun, let's get the high voltage tester out and see what these caps are doing. So here we are. If you don't know, this is a device which can put several hundred volts DC across a capacitor, and it measures any current going through the capacitor. It should be 0, of course, because capacitors block DC. If this shows any kind of reading here at all, the capacitor's leaking. It should stay at infinity here. So we're connected up, so let's turn on, and whoa, that is absolutely amazing. That's 500k, the capacitor, which should be infinite. So even if this needle was sort of down here, that would be a reject capacitor. The fact that it's over here shows this is really badly leaking. Right, well, we don't need to prove it, but let's do the other one. There we go, even worse, look. God, that's like a 1k, 100k, 120, 200k. That's absolutely useless. So there we go, those caps were completely shot. So I think I'm going to replace this capacitor too. Why not? It would be a shame to replace every capacitor in here apart from just that one, so I'll do that. The other thing I want to do is to replace this rather unusual mains, 2-pin mains plug here with a more standard figure of 8, it's called, I think, little mains plug, so we need to somehow cobble that into there. And we're also going to replace, we've got 2 banana plugs here for with a signal in. I'm just going to replace that with a single phono socket. So let's do that cap first. Now, what cap is that? Oh, that's this one here. So that's 0.1 at well, we'll put a 600 volt cap in there. So we'll replace that 0.1. It's 150 volts it says, but we'll replace that with a 600 volt cap. And I think we'll measure the leakage on that. Why not? And see if it's a bad cap or not. But as I say, it's a shame to replace every cap and just not replace that one. So let's do that. Okay, so the object, I've made a little plate here, a bit thicker than I'd like it, but I didn't have any thinner material. So we're going to, it needs trimming down a bit. Yeah, we'll trim it off here somewhere, and then we're going to somehow get this into here. Bit of metal bashing, and then we will drill the holes here and here, and then bolt that plate back on to the right. Okay, well, let's get on with the metal bashing. Well, I thought you might like to see this 1.1 microfarad capacitor here. There we go, press the button. Oopsie. Oh, look at that, leaking, increasing. That's not a short circuit, but it's only 300k, that resistor. So again, terrible. So I'm really pleased we replaced that. Interesting, isn't it, how these capacitors go completely leaky after a period of time. Good. Now, whilst I'm running the camera, I've made up this plate here. Took a bit of metal bashing that. And then this little figure of 80 thing goes in here. So I'm just going to put the screws through there and put that in, and then we can put that in properly. Right, there's the little panel I've made. It's taken a ridiculous amount of time actually. I reckon I spent nearly 2 hours just making this, and it's had to be filed to fit the hole in the chassis here as well, and has to be positioned exactly right, centralized, but you know, got there in the end. So I'm now ready to fit this, and we can get the mains sorted out again. Okay, there we go, 3 hours later. The figure of 8 connectors in, and I've also put the phono in, and that wasn't particularly easy to get in either, because it's a little bit tight in here. There it is down the bottom there, and I've put this piece of screen lead from it to the connectors, the pins on this connector here, which is was the original signal in cable. Not sure what these other four are, but that's the signal in there. So there we are, we're kind of ready. Everything's done. We're now ready just to power up and see if the thing works. I mean, of course we can start testing all the resistors and making sure they're in tolerance and that sort of stuff, but you know, you end up with an amp that's not really the original amp, and resistors being a little bit out of tolerance, not the end of the world, but capacitors leaking is very important because it puts DC through where it shouldn't go. So I think we've done kind of the most bang for our buck on this amp, I would say. So let's see if it works. We should be so lucky. Okay, we're all set up for the test here. We have the amp connected to my dummy load here, 8 ohm load, and that's going off to my oscilloscope, which I'll show you in a moment. And we have the signal going in here from a signal generator, and it's switched on. And if we have a look at the oscilloscope, you will see we have a signal there, and as I turn up the signal generator here, you'll notice the signal gets bigger, which is nice. Let's have a look to see how much this is putting out, and obviously it squares off at some point, but we're getting about 5, 10, 15, 25, 30 at a push there, volts peak to peak. So let's, obviously it'll be a bit distorted at that, but that's fine. The maximum this can put out is 30 volts peak to peak, and here's how you calculate the power. Look, you take the peak voltage, which is half of 30, 15, multiply it by 0.707, equals, that's the DC equivalent of that AC waveform. So power is V squared over R, so this is now the DC, so we multiply that by itself, 10.06 times 10.06 divided by the load resistor, which is 8, and it's given 13.3 watts on a good day, and it's advertised as a 15 watt amplifier, so this is actually pretty much what I would expect. So it's given 15 watts. Let's see what the frequency response is like. We won't push it at full power. Let's just make a sensible thing there. So we've got like 2 divisions, look there. Now we're on, what are we, 100 Hertz, 200 Hertz at the moment. So let's go up to 2.5 kilohertz. So you can see that's completely flat. And now, well, let's go back down to 1 kilohertz here. That's 1 kilohertz flat. Now let's go to 10 kilohertz. Completely flat, look, which is great, just what I'd expect. And let's see what it'll go up to before it starts to roll off. Now we're up to 20 kilohertz, look there. Just rolling off a touch, look. 30 kilohertz. So it's just down a little tiny bit at 30 kilohertz, look. So we've got plenty of way above the range of human hearing that. So let's go down now to low frequency again and see what it's doing down at the low end. Now that is 300 Hertz. Let's turn this up and go down to 100 Hertz. So that's 100 Hertz there. As you can see, dead flat, which is nice. And we'll come back down to, that's 50 Hertz, completely flat, look. And so frequency response on this is great. That 100 microfarad capacitor we put in the tail there would have helped. Look at that, completely flat at 30 Hertz, 20 Hertz, just gone off a little bit I think, and then 15 Hertz. Again, that's just down a touch there. 10 Hertz. God, what a fantastic frequency response. Look at that. That's hardly down at all. Just to prove it to you, I'll go to 1 kilohertz. There you go. So that's 1 kilohertz. And that's 10. There's hardly anything in that. It's fantastic, isn't it? Look at that. My sequence generator won't go down low enough, so that's really very good. And there's no noise or anything on there. Let's just go a bit higher. Stop this. There we go. Nice clean waveform, look. No noise, no hum. Beautiful. So there we go. I think we can say that's job done on that. I've put a spot of araldite under these capacitors here to glue them down onto their brackets so they're not going anywhere. And I'm really delighted with that. It's taken a long time, but we have got one of these quads back up to full spec, I think. Now obviously we could put new valves in and stuff, but yeah, that does start to get stupidly expensive. And it's working, so let's leave well enough alone. Very happy with that. So all we now need to do is to do exactly the same to the second one, which will take me less time. This resistor here, by the way, I'm not going to touch it, but it's hardly putting out any. Yes, it's hot to the touch, but not stupid. So I'm not worried about this capacitor or anything getting hot. It's no, that's cool to the touch, and it's not an electrolytic capacitor anyway. So I'm happy with the clearance there. I'm happy with the clearance here as well. There's a fair bit of clearance between those two. Don't worry about me putting my fingers. I often get people say, you shouldn't put your fingers in an amplifier. I always laugh at that. I kind of know what I'm doing, you know. A bit like saying to a mechanic, oh, that engine's spinning, you know, you shouldn't have your head under the bonnet. I thought you might like to see the capacitors out of the second amplifier, so I've now taken the caps out of there, and there you go, look, there's a leakage on that, absolutely terrible. Now I'll just put the camera down and put the other cap in and show you that. There's the second cap, haven't tested it yet. Oh, not too bad that one, see, that's a lot better. Still leaky, definitely to replace that, and that's 40 meg ohms, which might seem a lot, but it's still DC leaking through that capacitor. And as you can see, I don't know if you can see that meter creeping up, look, creeping up. And if I were to heat up that capacitor, that would dramatically increase. I don't know whether you want to see that for a bit of fun. Yeah, why not? Let's just get the heat gun on that capacitor and see what happens to that leakage. Okay, I've only got two hands, but I'm just going to put the heat gun on it and then I'll press the button. Heat gun's not on very high, got it on sort of fairly low. We'll just warm that capacitor up a bit. There we go. Let's warm that up now. Let's see what it's doing again. And look, see how's it getting warm? Look, see that needle creeping up? Look. As that warmth is seeping through the capacitor. So now we're significantly more. Remember, we were at 50 meg. We're now at 4 meg. 4 meg ohm resistance. So as this capacitor warms up, it gets more and more leaky. Let's just take that final signal capacitor out, the one that we replaced there on the good amp. We'll take that out of the second amp and see what that's doing, and then we've got a sort of full house really. But 5 out of 6 capacitors so far leaky. Okay, here's the 0.1 capacitor, and let's see what that one does. Whoa, look at that. It's 100k. Absolutely shocking. Let's warm it up a bit since we've got the heat gun handy. Okay, let's see what that's done to it. There you go, it's gone down to 100k, it's about 50k and getting worse. So that capacitor is very, very leaky. Terrible. Okay, so we'll just replace all those and away we go. So there we go, I'm happy with that. I hope you enjoyed that video. Quite an interesting one, I hope. I'm sorry it's a little bit long, but I hope you enjoyed the walkthrough on that. So I'm going to sign off now, and thank you for watching, and I'm going to catch you on the next video.